All right, today we're diving deep into the heart of modern power plants. Because the story of how we get our electricity, how we power our entire world, well, it's not just about burning stuff. It's a fascinating, century-long engineering quest for one single thing.
I mean, think about it. You flip a switch and the lights come on. Simple, right? But behind that switch is this absolutely massive, incredibly complex system generating a staggering amount of power, 24/7. So how does it actually work?
It always starts with a source of heat, sure. That could be natural gas, coal, a nuclear reactor, whatever. But the real story, the thing engineers have been totally obsessed with, is this constant, determined search for a single goal. Efficiency. That is the name of the game. How do you squeeze every possible bit of useful energy out of the heat you start with? How do you waste less and produce more? That is the quest we're going to follow. So, let's jump in. Our journey begins with the fundamental blueprint, the cycle that is the foundation for pretty much every major steam power plant on Earth.
So, Section 1, the power plant blueprint. What's the master plan for turning heat into electricity? Well, it turns out engineers had to make a tough choice between a perfect idea on paper and something that would actually work in the real world. See, in a perfect universe, we'd use something called the Carnot cycle. Theoretically, it's the most efficient design possible, no wasted energy. But it has some major practical problems. So instead, engineers created a workhorse, the Rankine cycle. It might not be perfect, but it gets the job done.
So what's so impractical about the perfect Carnot cycle? Well, the issue isn't the theory. It's what it does to the equipment. To make it work, you'd have to send very wet, misty steam into your turbine. We're talking about liquid water droplets hitting the turbine blades at insane speeds. It would literally sandblast them into pieces. So, to avoid destroying their multi-million-dollar turbines, engineers needed a better way.
And that brings us to this elegant solution, the Rankine cycle. It's a simple, continuous four-step loop. First, a pump puts water under a whole lot of pressure. Second, a boiler heats that water up into high-pressure steam, and then it keeps heating it into what we call superheated steam. It's totally dry. Third, that superheated steam blasts through a turbine, spinning it like a pinwheel to generate power. And fourth, a condenser cools the steam back down into water, ready to start the whole trip all over again.
And this brings us right back to our main quest. We need a way to measure how well we're doing, and that metric is called thermal efficiency. You could think of it like a grade on a test. It asks, of all the heat energy we pumped into the boiler, what percentage actually got turned into useful work by the turbine? The entire goal here is to get that grade as close to 100% as we possibly can.
So, what's our starting grade? For a basic, no-frills Rankine cycle, it's 26%. Yeah, let that sink in. That means for every 4 truckloads of fuel you burn, only 1 actually becomes electricity. The other 3 are just wasted as heat. So, yeah, the engineers had a lot of room for improvement.
All right, so this is where the adventure really starts. How do you take that pretty said 26% and start pushing it up?
The core principle is actually, believe it or not, pretty straightforward. To make the cycle more efficient, you have to make the temperature difference between the hottest part and the coldest part as big as possible. That means you either get the boiler even hotter or you make the condenser even colder. And that's exactly what engineers did, step by step. First, they focused on the cold side. They lowered the pressure inside the condenser, basically creating a vacuum, which let the water boil at a much lower temperature. That one change? Boom! Efficiency jumps from 26% to over 33%. Huge! Next, they pushed the hot side, superheating the steam to a blistering 600 degrees Celsius. Another jump? Up to 37%. Finally, they cranked up the pressure in the boiler itself, way up. And that got them all the way to an impressive 43% efficiency. We are making serious progress now.
But of course, there was a catch. As they pushed the pressures and temperatures higher and higher, they ran smack into a familiar foe. That very same problem that made the perfect Carnot cycle a no-go in the first place.
So now the quest took a new turn. It wasn't just about raw power anymore. It was about being clever and fixing the problems that our own improvements had created. And there it is, our old enemy, moisture. By jacking up the boiler pressure to get more efficiency,
we were accidentally making the steam coming out of the turbine much, much wetter. The moisture content jumped to nearly 20%. Again, we were facing the prospect of shredding our turbine blades. So the quest was at a crossroads. How do you get all the benefits of high pressure without that destructive moisture?
The answer came from two really clever engineering hacks. The first one is called reheat. Instead of letting the steam expand all at once, they do it in two stages. They let it expand a bit, then pipe it back to the boiler to heat it up again and dry it out, before sending it through a second turbine. The other trick is regeneration. This is just brilliant. You bleed off a little bit of the hot steam from the turbine while it's still working and use it to preheat the water before it goes into the boiler. It raises the average temperature of the whole cycle.
And what happens when you do both of these things at once? The efficiency just skyrockets. With both reheat and regeneration working together, our plant is now hitting over 49% efficiency. We've almost doubled our starting point just by cleverly solving the side effects. But the engineers, they still weren't satisfied. The next great leap forward didn't come from improving the steam cycle itself, but by giving it a partner. It was time to team up.
Meet the combined cycle power plant. The concept is genius. You start with a gas turbine, basically a jet engine bolted to the floor that runs incredibly hot. Now normally, its super hot exhaust gases would just get vented out the chimney. We're talking heat over 500 degrees Celsius, just gone. But in a combined cycle, you capture that waste heat and use it to boil the water for a whole separate Rankine steam cycle, running right alongside it. It's the ultimate 2-for-1 energy deal.
And this is where you see the magic happen. Look at this. The gas turbine by itself, not that great, about 27% efficient. The steam cycle that it's powering, it's pretty good, around 41%. But when you put them together, using the waste of one to power the other, the total efficiency of the plant jumps to nearly 49%. It is the perfect example of the whole being way, way more than the sum of its parts.
This combination, this teamwork, is what brought us into the modern age of power generation. It allowed us to push efficiency to places that, just a few decades ago, seemed completely impossible.
So, after this entire quest, through superheating, reheating, regeneration, and now the combined cycle, where did we end up? We ended up here. The current world record for a combined cycle plant in Bouchain, France, is an absolutely mind-blowing 62.2% efficient, from a starting point of 26% to over 62%. That is nothing short of a triumph of engineering. We've come so far. But now, we're getting really close to the absolute physical limits of materials and thermodynamics. The original quest for efficiency is nearing its peak, and that leaves us with a new, much bigger question. What's the next great quest in how we power our world?